Hello, welcome back to the AM Medical Summit. I'm Debbie Holton with ASME, and I'm very proud to bring you into this next session about a very important aspect of additive manufacturing that a lot of people don't always think about, which is post-processing. Yes, these parts typically do not come off the printer ready to go, and so we're pleased to have Arushi Dakad from EWI in Buffalo, who is an expert in this field, here with us today to share some of her findings and take us from design all the way through the finished part process. So Arushi, thanks for joining us, and take it away.
Thank you, Debbie. Hi, everyone. Like you said, I'm Arushi, and I'm calling from EWI, talking about post-processing. And just like Debbie mentioned, I think I have a whole slide on that of how it's an important part, and we end up missing that in the beginning part because it's not exactly the most fascinating aspect of AM. So before I go into parts and design and surface improvement, a little about me and EWI. My degrees are all over the place, industrial engineering and mechatronics, but I've worked with biopolymers in the past. And at EWI, I have been working with post-processing methods and especially surface topography measurements and other NDE inspection methods for the last 3 years. EWI is an it's an applied manufacturing R&D company. We specialized once upon a time in welding, forming, microjoining, and though we still do all of that, we also took a dive into the AM world about a decade ago. In terms of our area of expertise relevant to the topic is we do a lot of large-scale DED. We have a lot of those different machines, powder, wire, different sources of heat. We also do a lot of non-destructive inspection techniques ranging from X-ray CT to ultrasound and to surface topography methods like the machine behind me, which is a white light interferometer, and then confocal microscopy, etc. We also have a lot of material science experts in-house, separately for materials and a few for polymers, some for composites. I am not either of those. I am the non-destructive person speaking here. So back to the topic about AM, generic stuff. Everybody knows here, I'm assuming, that additive is layer by layer as opposed to most traditional methods, which are more subtractive in nature. So we go from a tiny little form of raw material feedstock, which can either be a powder or a resin or a wire, into a 3D part. And depending on the material that we're talking about, either a technique already exists or it's in development, or there is, even if there is already a technique, somebody else is improving it, making it either smarter or faster or better in production, or removing those few design allowables that AM doesn't allow. So there is just so much going on in this area. That being said, while there is so much in the fascination world and the research area of it, there isn't much happening on the production side. Even large industrial companies are in their pre-production stages for most of their parts. There are a few parts that have gone into production and have actually made it to actual things, but not too many. So in terms of advantages, of course, because we're building from one small grain size or a resin to a larger part together, we have so much more freedom in defining the geometry. It doesn't have to be subtracted from a block anymore. It is not restrictive to a mold from which you have to remove a part. So in that sense, there are so many geometric limitations. There's so many more geometric freedom, design freedom that we get here, which is also the same thing where I'm saying while it's great in the manufacturing side, the inspection world is still yet to get ready for that much complexity. So there is sort of a communication gap there. That is one of the limitations that I'm talking about. And another thing that I mentioned here was how AM allows us to reduce the number of moving parts. I have one sample here that shows that. So you can see this part, it's one single piece. This is all printed together. And if you can see it, there are tiny little small pieces inside. Think of it like a gear assembly, but not exactly the gear design. But it rotates. All of it rotates. It was built in one single piece, no separate builds, and aligned together. So it's the moving parts, yes, but they weren't built separately. So less confusion, less things to test there. And in terms of geometric design opening up, there was another part here. If you see, it's got really sharp edges. It's metal. It's probably titanium. And you see those crevasses in here. If you can see the creases in line there, and how thin the part exactly is, that would be very difficult to build via a traditional method of any form. This is not exactly a part for use. This is just a part for a demo part. So I can't say any use to it. Also in terms of geometric design, how we can make tiny meshes. So this is an internal mesh. It doesn't really, one of those lattice structures that doesn't exactly have proper thing. I forgot the word for it, but this is the kind for which cells should be able to grow on it. I don't really remember the words anymore for that part. Forgot that word for a while. So that is generic stuff. And then more on this is how we were saying the workflow. So depending on what you want to build at the end of the day. For example, I have a laptop in front of me and I want to make the keyboard keys out of polymer and I just want to print them and I want to fix them into the laptop. So I don't need a metal. I'm good with a polymer there or a composite, whatever is cheaper. And design and functionality, I mean, I can think normal cube blocks like they are, but they could be round. They could be any other fancy shapes. So they can be in forms of the letters themselves in terms of functionality. So that's sort of a random example of how, depending on the feedstock and the design, you design you choose the AM technique that you want to use. It might not always be in this straight format. Sometimes you have a particular AM machine in-house. You want a particular part that was built traditionally once upon a time, and you want to convert to AM or switch to an AM platform, and you're just exploring it. And you care about that the structural integrity either remains the same or improves. Its mechanical properties, its chemical properties, corrosive properties, all those properties remain the same. So sometimes that is direct of this is the, I mean, if you're starting out first, then based on the feedstock and the design, you can choose an AM technique, but sometimes it is the other way around. But irrespective of what we do there, almost every single AM part has to go through post-processing. If it's a metal part built in a closed vacuum chamber that had heated up temperatures all the way up to 800 degrees Celsius or more, like electron beam melting methods, then removing that powder surrounding it can be a real pain. Then for almost all powder bed methods and even other wire methods, you build on a base plate, a block, a substrate of it. And because the part itself is welded to the substrate, you need to cut it off. When you cut it off, you're introducing new residual stresses over there. Depending on the application, the part, whether you had supports or you didn't have supports, you can stress relieve it and like give it some heat treatment before you cut it off the plate. Do more heat treatments after you remove it off the base plate in order to reduce the residual stresses on the newly exposed cut-off surfaces. And if there are any internal pores or lack of fusions in there, and this is very specific to AM, metal AM there. So there are ways for those heat treatment, and then comes the surface, improving the surface itself. Now AM surfaces, and this is not an example I can show you by showing a part, are very rough compared to other surfaces, other directly out of a manufacturing process surface. It needs a lot of additional work depending on what the end use is. Sometimes the end use is, say, it shouldn't corrode very fast. And then if your part has way more surface area than the flat surface would have, then you want to improve the surface to reduce the surface area over there, to reduce the locations where there might be corrosion. Similarly, surface and depending on how rough it is, it can also impact its fatigue life and its mechanical strength. For example, I have pictures of that later, so I guess I'll talk on that later for surface improvement. And for all of those post-processing methods, and I mean, I'm trying to tie in exactly with respect to what post-processing or after what post-processing, what are you inspecting for? So mechanical testing might be after the heat treatment, substrate removal, but it's not going to be on the final part. It's going to be on one of the initial parts or supplementary samples built only for that purpose. Then there is destructive analysis, where you just cut open the part, see how it is inside for porosity, how it is, how the microstructure inside looks, because material scientists are usually very well read to be able to tell whether microstructure, how the structure relates to its functionality. But again, you can't do that on the final part. So we have non-destructive evaluation like X-ray CT, ultrasounds. X-ray CT has its own limitations at times, depending on the geometry of the part, of what the material is, what its density is, because X-ray light actually has to pass through it, the complexity of the part, and if you have a multi-material part, which is many different, say a carbon-based polymer and the nickel-based alloy in the same thing, and you want to see both things in the CT scan, it can be really complex. It can be really difficult to get both things in one single CT scan. And these are things that you only realize when you do them for a while. And then back to surface topography, my favorite topic. So inspecting that surface that we made. So if we made parts like this one back here, and I want to know how the surface roughness is all the way on the inside, but I want to get about 500 times the magnification of the area in there and then measure it. I am restricted because I can't use a contact-based method to go in there, and I can't, and I have limitations on what other methods I can use. And again, more on that later. So there are a lot of limitations here. And so yes, we can do very cool designs with AM. We can, the system allows for it. There is something called design for additive manufacturing, but there is nothing for design for inspection. And sometimes that can cause a problem or increase the number of iterations that somebody would take in deciding whether a geometry and a particular material to reach its production line or to reach its almost end use as of now. So yes, I've talked about this already, of how surface texture has so many impacts, mechanical performance. So the roughness of a surface, basically think of it like mountains and valleys. The valleys are stress concentration points which can affect the mechanical performance. So if a part is going to crack, it might just crack faster or sooner if those valleys are very, very deep or way too many right next to each other. That mechanical performance, it might be fine in the first 100 times it's been exposed to its elements, the parts elements. For example, if it has to resist heat or if it has to bear a certain amount of load. But long-term load bearing capabilities and durability might not work together. So that's a different thing. So it would be completely dependent on what the end use is, what the application is. Then there is addition. If you want two surfaces like the gear module we had of being right next to each other and you care about the finish. So if these parts weren't built in one single block, but if they had to be built separately and they were much rougher than they are, the movement won't be smooth. And again, this is a toy right now, but when if you're making a whole gear assembly for a car, you want it to be reliable enough to have the exact same response, every single time. That reliability can be dependent, a problem. If your surface isn't smooth enough, if it isn't predictably repeatable enough. And then the same thing with fluid flow. If you have, say, impeller channels with or heat exchangers with gas flowing inside it or fluid flowing inside it. So, so many more problems over there. So surfaces are very important, is all I'm trying to say. And so in my work here, we've had to deal with industries ranging from oil and gas to aerospace to automotive and biomedical devices. I'm not saying that's the end of the world that cares about surface roughness. This is just the beginning. So surfaces. So these are some examples of AM surfaces. These are all metal surfaces. There are two different powder bed methods. The most commonly used one and the most famously known is laser powder bed fusion, where there's a laser light source and there's a powder bed and the laser builds up parts. The chamber in which it's built up is not room temperature low, but it doesn't go higher than 150, 200 degrees Celsius ever, as far as I know. And the chamber can be filled either with inert gas or with just a closed air chamber so that there's no disturbance in there. But then there is also E-beam, electron beam, where the machine's closed in. It's under vacuum. The powder is built under vacuum. It's tiny little electrons building the entire part slowly by slowly. And here the temperature increases all the way up to 800 for Ti64, and then similarly higher depending on the material it is. So here the powder size is slightly bigger because you don't want it to interfere with the optics of the machine, and which means the parts are rougher. So what I'm trying to say is that the heat source, the raw material itself, the process parameters that are used in order to build the boundary of that particular geometry that you're trying to build. So that would vary from geometry to geometry. Because depending on the material and how closely the geometry is put together, you might be dissipating heat well enough, uniformly enough, you might not be. So many complications there, and post-build steps. So all those variables. And like I said, these are all powder bed parts. I'm not even showing DED parts because they are usually much rougher. Why DED parts are much rougher, and they're not as repeatable on the same patch of surfaces. They can vary drastically in roughness from one area to another area. And so on these four geometries that I'm showing, A is electron beam powder bed, C is a laser powder bed, as built right out of the machines, no functioning done on them. And these are all about 1 by 1 millimeter areas. On the right side, the right two images, B and D, are finished surfaces. So, and there are different finishing techniques. I don't think I'm allowed to tell the names of those. But so in the top one, you can see that there was a somewhat mechanical process to that surface improvement method. So you can see layer lines. So they can either be layer lines or machine lines, depending on where that came from. And then the second one, that is the bottom right corner, D image, which looks very cracked up, was a more chemical method that removed a significant amount of material from the top of the surface. So surprisingly, the bottom one actually performs much better in this particular case. But this is how surfaces can really vary. And while none of these would be ideal, you want a smooth surface like the top right one, but you also want it to not have weird valleys in the middle of nowhere like this, because though it is 90% good, 99% good probably, that one tiny little thing can make it fail faster than this might fail. So these are things, and because they're at a micro level and we can't see them, micro and a nano level at times, we can't see them. So it's difficult to examine them. And with AM and with geometries such as these, it can be very difficult to get an idea of what the exact surface looks like. More on the measurement limitations here. So in terms of measurements, so this is what I meant by peaks and valleys, mountains and valleys over here. And if you'd have a reference point. And so this is an isometric view taken from, this is from a website, but this is how a 1 by 1 millimeter area at an isometric view, an AM surface would look like, where there is no symmetry as such over here. So traditional surface roughness measuring methods, and the most commonly used in production everywhere, are tactile methods, contact methods, profilometry, where a stylus like this with the tip measures everything. The limitation of the machine depends on the size of the tip over there, and you might miss the smallest peaks in tiny little areas such as these. Can be very difficult to measure. For example, the tactile method that you see up there is limited by the size of the tip. And while I can make a tip probably go inside, it won't work in a straight line. It won't have a linear path to go through. So there'll be so much error that is not measurable exactly, and so you can't account for it. And similarly, other methods, non-contact aerial methods like focus variation there, which uses optical light, multiple different images at different Z levels that it stitches together in order to give you a view like you see on the right image. And laser confocal gives you aerial images, yes, but uses a laser light, reflects it back, and that computes it into that X as a function of Z and Y sort of map on the right. Coherent scanning interferometry, like the machine behind me, a white light interferometer does a similar thing. It's better for reflective surfaces, but it has, I mean, it's a nice machine. It just has the method itself has a slightly longer learning curve to it. And computed tomography, which is X-ray. So this is a new experimental method that is yet to be used beyond academia. But where the idea is that if an X-ray CT scan has a resolution good enough to see the surface, then can we use that to measure surface roughness? Hence, eliminating the entire problem that I'm talking about right now of how if there are deep valleys or very, very complicated surfaces that are difficult to access at a normal angle, they can be measured after they've been scanned. So if you're taking aerial measurements, they would be measured in different ways. These are some ways in which they are measured, quantified. So the height of the peaks, the depth of the valleys, how close those peaks are to each other, how close those valleys are to each other. Is the surface skewed in the sense that does it have more peaks than it has more valleys? Does it have a lot of outliers like in the initial images that I showed you? And just simple arithmetic mean, which is used most commonly. So this is sort of a little extra. If you have any questions on this, let me know. And I'll move on to closing almost. So how I mentioned that all these different measurement techniques have their own limitations. Being able to access inside a part. For example, in a mesh like this, it's small enough and small enough that if I want to measure it via a CT scan, the surface roughness of it, it's so tiny. I'm never going to get a resolution good enough in order to be able to get the surface in each little surface up with great quality. So I can't use a CT for it. I can't use focus variation for it, an optical method for it. I am not going to be able to access it via laser powder bed, via laser confocal either, which is a laser method. And I definitely cannot use a contact method for going in there. But then the question comes back to, do I really care about what the surfaces look inside? So depending on what you want the end use to be, how you've designed the part to be, sometimes thinking of measurement and the inspection part beforehand, especially when you're designing it, and designing it such that it is accessible later for inspection can really make the entire starting to ending cycle become less repetitive. Just the way when we design parts for AM, we keep in mind how we are going to orient them right when we design them, because we know that if we don't decide how to orient the part when we build it, we're going to have a lot of complications and a lot of errors there. So similarly, inspections should be kept in mind, and how you want to inspect it and what you want to look for at the end of it should be kept in mind in the design phase itself. And while fancy tools like topology optimization are great, we don't account for these there as well. So just some things that have to be taken in account. So I'm one of those people who has to measure them and sometimes design them. So we've had to face both worlds, and I don't know a lot of people that have had to do the same thing. Closing in with challenges that we've faced with surface topography. This is again sort of extra of how these methods do exist, but measurement methods were made for traditional surfaces, and AM parts are significantly rougher and non-repeatable from like one millimeter patch to another millimeter patch to one geometry to another geometry. And hence it can be very difficult to measure them and to know that your every measurement is perfectly error-free. That's it on my topic. Any questions? Thank you.
Thanks, Arushi. Great presentation. Love seeing the parts on screen as well, as I know our folks did. And so we've been getting quite a bit of questions in the chat window. So we're going to go ahead and break to the Q&A and answer some of those questions right now. So thank you.
Great. Thank you, Debbie.